Now that we understand the structure of atoms, we can put the atoms together to make molecules and ionic compounds. And what's going to hold the atoms together is chemical bonds. Why do atoms bond at all? Everything happens to give the lowest possible energy to the system. We started our study of stability by looking at the stability of the noble gases, and we saw that they were stable because their valence orbitals were full. All the other atoms are going to bond in order to attain this very stable electron configuration, to be isoelectronic with the nearest noble gas. Now, I've already introduced you to two very different ways that can happen: ionic bonding and covalent bonding. Let's briefly review ionic bonding. Our focus will really be on covalent bonding in this chapter. So we looked at ionic bonding, which are the attraction between oppositely charged ions. And I've shown you this scheme, or a similar scheme, a number of times. There's my favorite ionic compound, sodium chloride. What holds that crystal together, what holds the solid together, is the attraction between the oppositely charged ions. And you remember those lines are imaginary. They're not really there at all. It's the attraction that holds them together. Now, how does that form in the first place? We said that ionic compounds were formed when we had a metal and a nonmetal together. That's how we recognize it from the formula. Now that we know about periodic trends in ionization energy and electron affinity, it makes more sense that a metal with a nonmetal will make an ionic compound. In the ionic compound, the metal loses electrons to become a positively charged ion. And we saw that worked because the metals have a low ionization energy. It doesn't take much energy to remove the electrons. In contrast, the nonmetal gains electrons to become a negatively charged anion. And that's because they have a favorable or high magnitude electron affinity. So when I have an atom from the far left side of the periodic table with an atom from the far right side of the periodic table, the electrons actually transfer to make ions. And then those charged ions attract each other. Let's look at covalent bonding. In covalent bonding, you learn to recognize that when we had a nonmetal with a nonmetal, two atoms both from the right-hand side of the periodic table. So neither one of them wants to lose an electron. What they're going to have to do instead is share electrons to get their full valence orbital. And when they share a pair of electrons, we call that a covalent bond. A covalent bond is a pair of electrons simultaneously attracted to two nuclei. You'll remember that covalent bonds are only in covalent or molecular compounds. There are no covalent bonds in ionic compounds. So let's look at the formation of the simple covalent bond in the simplest molecule possible. This is a picture of the bond forming in H2 molecules. Why does it exist as an H2 molecule instead of two separate hydrogen atoms? On the far right side of the diagram, we have two separate hydrogen atoms, and they've got a certain amount of energy. But what happens when we let the distance decrease, when the distance between the nuclei gets smaller and smaller, the energy starts to go down. That's because the electron from one starts to attract the proton from the other. And the proton from one starts to attract the electron from each other. So I start to get stabilizing attractions. That energy goes down and down and down until I get to a very small distance, at which point the energy will start to rise up again. When they're that close together, the nuclei actually get close to each other, and those like charges start to repel. So the bond length in a hydrogen atom from the center of the bond length in a hydrogen molecule, the distance from one hydrogen nucleus to the other, is a result of the balance between the attractions between the protons and electrons and the repulsions between the protons. What we've seen here is what we would call a nonpolar covalent bond. The electrons are going to be shared equally between the two hydrogens. And why wouldn't they be? But sometimes we find covalent bonds which are polar. In other words, the one end of the molecule is one end of the bond is a little more positive and one end is a little bit more negative. In other words, the atoms don't share the electrons equally. So here's an example of HCl. Now, in aqueous solution, that acts as an acid and dissociates, but pure HCl gas is covalent. And it turns out that chlorine has greater attraction for the shared electrons in the bond than the hydrogen does. We can show that in two ways, and they're illustrated in figure 7.7. First, we can show it as a vector for you physics fans in the house. The head of the arrow points to the more negative ends, and we put a little cross on the more positive end. See, that looks like a little positive sign there? Another way to show the same thing, and I've showed you this before, is to say that one end is a little bit negative and one end is a little bit positive. That Greek letter lowercase delta means a little bit. Now, how do we know when atoms have different pull for shared electrons? How do we know when we'll get one end of the bond a little bit more negative than the other? Well, we're going to look at a property that tells us how much pull the atoms have for shared electrons. And you biologists probably know that that property is called electronegativity. Just let me jot down what I said in words. Electronegativity is a measure of the attraction for shared electrons in a covalent bond. Now, this table from your textbook shows the trends in electronegativity, but we proved in chapter 6 that our understanding of atomic structure means we don't need to remember that. We can figure that out ourselves. What I can see as I go across the periodic table, the most important structural feature is the increasing positive charge on the nucleus. So as I increase the positive charge on the nucleus from left to right, greater positive charge should have greater attraction for the negative electrons. That's Coulomb's law. So that's why electronegativity increases from left to right. As we go down the periodic table, the important structural feature is that the valence electrons are in higher and higher energy levels further from the nucleus. So if I share electrons with another atom at the valence level, which is the only level where there's room, the higher the valence level, the further from the nucleus and the less attraction for that shared electrons. So the electronegativity decreases down the group. You could figure that out. You didn't need somebody to label this diagram. So when I put those two factors together, it looks like the most electronegative atoms are in the upper right-hand corner. You will notice that one group is missing from the periodic table. There are no noble gases here. Why is there no electronegativity reported for noble gases? The definition of electronegativity is the attraction for electrons in a covalent bond, and noble gases don't make covalent bonds, usually. So their electronegativity is undefined. Now, there are numerical values of the electronegativities given here. For example, fluorine is 4.0 and hydrogen is 2.1. We are very rarely ever going to need them. You can know which atom is more electronegative based on a periodic table and your understanding of periodic trends. But in all things, of course, if you ever did need them, of course, I would provide those values to you. I couldn't ask you a question that's impossible to answer. So let's relate electronegativity to the bond types. How does it relate to nonpolar covalent bonds, or a polar covalent bond, or an ionic bond? Well, let me remind you of the three kinds of bonding. My voice said it, but I haven't written it down. Nonpolar covalent bond, the electrons are shared equally. In a polar covalent bond, and I put covalent in brackets there because I usually leave that out, I just say polar bond. The electrons are shared, but not equally. Electrons are shared unequally. And as we said for the ionic bond, we don't share the electrons. The electrons are actually transferred from one atom to another to make ions. I'm going to give you examples of bonds of each type, and then we're going to relate that to the electronegativities of those atoms. The example I gave you for a nonpolar covalent bond was hydrogen. The two atoms are exactly the same atom. They must have the same pull on electrons. They must have the same electronegativity. So the electronegativity difference is 0 between those two atoms. The example I gave you for a polar bond was HCl. And if you looked up in the table, you could see that the electronegativity of hydrogen is 2.1 and chlorine is 3.0. You would probably have to look this up because hydrogen kind of floats on top of the periodic table, so you can't use periodic trends to know how that fits in. We can see from those electronegativity values that chlorine is indeed more electronegative than hydrogen. And if I do a calculation of the electronegativity difference, delta electronegativity, 3.0 minus 2.1 is 0.9. Finally, my favorite ionic compound is sodium chloride. And don't you dare draw a line connecting those two atoms. Those lines reflect covalent bonds, and there's no covalent bond in an ionic compound. I'm just going to write the electronegativities here from the table. Sodium has a value of 0.9, and chlorine has a value of 3.0. So the electronegativity difference here, 3.0 minus 0.9, is 2.1. Here's the trend that we're developing. For a nonpolar covalent bond, there's no electronegativity difference between the atoms. Then when I increase the electronegativity difference, the electrons get shared less and less equally. The more electronegative atom has more pull on the shared electrons. Finally, if I make the electronegativity difference between the two atoms great enough, they stop sharing. One atom completely rips the electron from the other. The electrons are transferred, and I get ions. Now, in the old days, we treated covalent compounds and ionic compounds like they were completely different things. But what we see now is that there is a whole bonding continuum. There is a range of bonds based on the electronegativity difference. So I've made a little number line here with the electronegativity difference on it. If I had 0 electronegativity difference, that would be a nonpolar covalent bond. I chose 4 at the other end because the most electronegative atom is fluorine, and it has an electronegativity of 4. So at the far end, if I had an electronegativity of 4, that would make an ionic bond. For sodium chloride, it was only 2.1. Now, where can I fit the rest in? In the intermediate electronegativity differences, I'm going to say between 0.4 and 1.8 is where I'll get a polar covalent bond. So as I increase the electronegativity difference, it goes from being nonpolar to polar to ionic. I get increasing ionic character as I increase the electronegativity difference. One last thing to show you here. Although to be perfectly nonpolar, the electronegativity difference is exactly 0. If the electronegativity difference is small, say less than 0.4, then that's going to be effectively nonpolar. The polarity would be so slight, it's not worth worrying about. Okay, in the next video, we'll start to stick these atoms together and draw Lewis structures for molecules.